Hi, this is Gordon Parker from Michigan Tech University, and this is the second video in a two-part series where here we will look at the characteristic root errors for simulating first-order dynamic systems, and that will give us some guidance in terms of how to set the integration time step to get accurate results. So here we go. So again, we're going to look at Euler integration and characteristic root errors. So let's say that we have a first order linear system, x dot equals lambda x, and lambda is the characteristic root. Think of it as a pole if you'd like. And we'll have an initial condition on this dynamic system that at time equals 0, it's x0. Now the solution to this is x0 times e to the lambda t. And what we want to do is compare that to another solution that is x0 times e to the lambda star hn. So t has been replaced by hn, and we have a approximate characteristic root lambda star. Now, recall Euler integration from the first video in this two-part series. That was xn plus 1 equals xn plus h times fn. Now fn is just lambda xn, so we can now write an expression for xn plus 1 using our example above. We have xn plus h times lambda times xn, and we can simplify this a bit as so. So we have this quantity times xn, and now what we'll do is compare the exact and Euler solutions at the various samples. We have samples at n equals 0, 1, 2, 3, all the way up to n. So let's just make a little table. Here's samples on the top row, and then how about we do the exact on the second row, and we'll look at this Euler sequence on the last row. So for time equals 0, everything is x0. For this first sample point, the exact solution is x0 e to the lambda h, and the Euler approximate solution is this, x0 times the quantity 1 plus lambda h. Now at the second time step, the exact solution is e to the 2 lambda h times x0, and the approximate solution is this. And now we just have 1 plus lambda h squared. Then we have a third sample point. We can keep doing this. So here's the approximate Euler solution, and now it's 1 plus lambda h cubed. And that's the third sample, and then dot, dot, dot. And we can go all the way to the nth sample, and it's useful to write that out. So e to the n, squeeze it in there, lambda h, and x0 times 1 plus lambda h to the n. Now if you look at those two rows and you focus on the n column, then we can do a comparison of the exact and Euler solution. So the exact is e to the lambda h to the n at every sample point, and compare that to 1 plus lambda h to the n. And I've thrown out the x0s because those are the same in both cases. Certainly those two quantities are very similar in the sense that it's two arguments raised to the nth power. So now we're going to play around with that a bit. So let me just rewrite this again. So we have this comparison of the exact versus the Euler. And now what we're going to do is say that there is an e to the lambda star h that's equal to 1 plus lambda h for some lambda star. And then that will give us some information about this characteristic root error. So lambda star is our approximate characteristic root. So let's come up with a definition for this characteristic root error. We'll define it as, we'll denote it as e subscript lambda, and it's defined as being lambda star minus lambda divided by lambda. So it's a fractional error in the characteristic root due to, in this case, Euler integration. Now if we play around with this expression a little bit, we can solve for lambda star h just by taking the natural log of both sides. And then, let's see, we can solve for lambda star. So we have 1 over h times the natural log of 1 plus lambda h. And now we can just substitute all this stuff into E lambda and get an exact expression for the characteristic root error. So natural log minus lambda h divided by lambda h. Now, this has natural log in it, so what we're going to do is approximate this for small lambda h products. So the first thing to do is to note that we can expand the natural log of 1 plus x into a Taylor series expansion or a binomial series expansion, depending on how you want to write it out. So we have natural log of 1 plus x, and there's x minus a half x squared, plus a third x cubed, minus a fourth x to the fourth, etc., etc. And we're going to apply this general expression to approximating the natural log of 1 plus lambda h from our characteristic root error E lambda above. So just to get that down, there we go. And now let's go ahead and do that. So the natural log of 1 plus lambda h, we'll just take the first couple terms, is approximately equal to lambda h, just replacing the x's in the previous slide with lambda h, minus 1/2 lambda h squared. And this is valid for the magnitude or absolute value of the product of lambda h much, much less than 1. So it'll converge. So E lambda is now approximately equal to, substituting this approximation into the previous expression, is this. We have a minus lambda h divided by lambda h, so we can do some cancellation, and this is approximately equal to negative 1/2 lambda h. And that is worth a circle, because that is the characteristic root error approximate for Euler integration, a fundamental property of simulating first-order systems using Euler. So let's play around with an example now. We'll use this example a bit as we move through the rest of this presentation. So we have a simple system with lambda equal negative 10. We're going to use Euler integration. And how about a time step of 100 hertz, or 0.01 seconds for h? Well, we can calculate our E lambda. It's approximately equal to negative 1/2 lambda h from above, and substitute in lambda, which is negative 10, and our h, and so we get a E lambda approximately equal to 0.05. That's a fractional characteristic root error. And what that means, if we back this out, right, if we solve for lambda star, that's approximately equal to lambda E lambda plus lambda. And we can simplify this a little bit, 1 plus E lambda times lambda. And so lambda star is about equal to 1.05 times lambda, and we do all that, we get negative 10.5. So our characteristic root error, or our characteristic root, is negative 10.5 instead of negative 10. Now what this means in this case is if we increase h, we're going to get a faster response. And this condition is true, this observation is true, as long as the product, lambda h, absolute value, is much, much less than 1. So you don't want to go using this correlation for when this condition is not satisfied. Now let's just look at, summarize a couple of the other integration methods that we looked at before in the other video. So here's Euler, so this is just a rehash of what we just looked at. So E lambda, yeah, negative 1/2 lambda h. But we can also do this for trapezoidal, AB2, etc., etc. So here's a review of trap. Xn plus 1 is equal to xn plus h over 2 and the quantity fn plus 1. So this was an implicit integration method because we needed information about f ahead in time, and its e lambda is 1/12 times lambda h quantity squared. And AB2 is xn plus 1 equals xn plus h over 2 times the quantity 3fn minus fn minus 1. And the characteristic root error is -5/12 lambda h quantity squared. Great. So now let's look at how to pick h for simulating a dynamic system that might have a whole bunch of characteristic roots, not just one. Although we'll still just look at the case for one to motivate how we pick the h in a simulation. And I also have to say that we're going to, for now, ignore stability. Typically, as you increase h, the integrated system can become unstable. And again, what we're looking at here is for lambda h much, much less than 1, and that is the system, the numerical integration method is stable. So it boils down to how much error can you really tolerate. That's how you have to make the decision about picking your integration time step. And of course, you have to weigh that against how long you want to sit around waiting for your simulation to run. So now going back to our example, if we look at Euler, and if we had a requirement that the characteristic root error had to be, let's say, 0.05, because that's what we were doing in the previous example, then we could back calculate an h, and that would be 0.01. Now we could do this for trapezoidal integration also. So let's say we wanted to compare Euler to trap, and again we had a requirement, the same requirement of e lambda equal 0.05. Now you back calculate from the 1/12 lambda h squared, and you would get a very different integration time step to satisfy that requirement, 0.0775. So what we can do is, in rough terms, if we had a range of characteristic roots, pick out the maximum characteristic root, lambda max, multiply it by h, raise that to the order of the integration method, and make sure that's much, much less than 1. And then you should have a reasonably accurate simulation. Of course, you can use the expressions above if you need more accuracy on your error analysis. So now we'll use MATLAB to compare Euler and trap integration using this particular example and these two time steps. So here we are in MATLAB. I have a script file I wrote to do this. And let me open that up. Here we go. And at the beginning, we just do a little bit of cleanup. Set lambda equal to -10. That's our pole, the characteristic root. Then we have he and ht in lines 7 and 8. Those are our time steps. And then make some sample points for Euler and trap. That's ne and nt. Those are our integers. And then some time vectors, te and tt, for the two Euler and trap integration methods. Now let's go to the next block of code. So here we do the actual Euler simulation. So we start off with just initializing all the data to 0, set the initial condition, and then run through the expression for xe equal to the old xe plus h times the lambda xe at the old time step. Then we do the trap. Now, a little bit of explanation here. I used the function that I derived in the first video in this series where for trapezoidal integration to make it explicit. And so that's why in line 27 there's a fraction quantity. And you can go back to that other video and see how that's done if you want the details of that. And I had to generalize it, of course, for this particular lambda, which in the other video was done for a lambda of 2 or 3, I can't remember which. Now here's the easiest part. There's the true solution. So now we have an xe for Euler and xt for trap, and we have a true solution. And all we have to do is plot those three things on top of each other. And I use some handle graphics here and some funny colors just to make it look a little jazzier. If you're not familiar with handle graphics, I would highly recommend that you dig into that a little bit. I created a structure here called H and then made a bunch of handles to various objects that were being created, and then changed the colors of the background and some things just to make it show up a little bit better on the video. So now let's go ahead and run this thing. So there's the plot, and let me expand it out just a little bit. So the red is the continuous exact solution, the blue is Euler, and that's at 0.01 seconds, and the green circles is trap. And notice that there's hardly any green circles. There's one at time equals 0, and then there's one between 0.05 and 0.1, and then there's one over there by 0.15 seconds. And yet it's the same accuracy as Euler, and that was done on purpose when we calculated the trapezoidal integration time step of 0.0775 to give us the same characteristic root error that we had for Euler integration. In a sense, we can see that all those approximate calculations work. Now what we're going to do is see how good that lambda star calculation really was. So let's go ahead and revisit our example. X dot equals negative 10x. We had lambda obviously is equal to negative 10. So let's just jot that down. H is 0.01, and we're using Euler integration with E lambda approximately equal to negative 1/2 lambda h. This is all review stuff. And that was 0.05 when we go ahead and substitute in lambda and h. Now, lambda star is about equal to 1 plus lambda times E lambda, and that was negative 10.5. So here's the question. How good is that lambda star? Right? We're using this approximation for E lambda. So how good is that? Do we have to really go back and use the natural log expression that we derived earlier? Well, let's just look at an example. And for this example, what we'll do is set x0, the initial condition, equal to 3. Write down the exact solution, 3e to the negative 10t, and also write down the sampled solution, exact, right, e to the negative 10 and h, and we can substitute in h and do some simplification just for our later coding practice. And then we have x star. So now we're going to use our characteristic root approximate, negative 10.5 t. And if we look at that in a sampled form, then we would have 3e to the negative 10.5 times nh instead of t. And we can substitute in our h, and we get this. So you can see it's a little bit different, negative 0.105 compared to the negative 0.1 above. And then we have the Euler integration version. So xn minus h times 10xn, putting in our lambda, and so that's equal to 0.9xn. So we're going to take these three expressions for the true lambda equal negative 10 and the approximate characteristic root lambda equal negative 10.5 and the Euler integration expression and compare them all in MATLAB on a single plot. And what we hope to see is that the x star exact, that is 3e to the negative 10.5t, should be very close to the Euler approximation xn plus 1. So let's go into MATLAB now, and I wrote a little script to explore this behavior. So let me open that up. And here we go. So in this block of code, we have the lambda being assigned negative 10, set the Euler integration step size 0.01, and then the sample points for Euler, the NEs, those are the integers from 0 to 20, so we're doing 20 steps. And then we also have the Euler time points, TE, so we just multiply the sample point array times the time step HE. Now the next block of code goes into the Euler simulation. So let me take a look at that. So here we initialize XE, the Euler simulation points, to 0, set the initial condition, and then just run through the Euler integration over the length of NE, so all 21 of those points from 0 to 20. And we just do your basic Euler integration, where we take the back value to create the new value of xe. Then we can create the true solution for, this is for lambda stars, so this is for our characteristic root that was approximated by negative 10.5. So that is denoted as x star, and it's an array that has the same size as the sample points for Euler integration. So we're using the NE sample points to calculate x star. And then we do the same thing for x true for the lambda equal negative 10. Very similar expression. Not much more to say about that, kind of boring. And now we go on to the plotting of all of this. And we're going to do something similar to the plot that was done in the previous set of code. We're using handle graphics. H is a structure, bunch of elements that point to different interesting things in the plot, labels and legends, etc., etc. And then flip around the colors a bit just so that we can see this a little bit better on the video. So let's go ahead and run this thing. Here we go, and there's the plot. Now the red line is the true solution, and what's interesting is that Euler, which is the dots, the blue dots, is right on top of the approximate characteristic root true solution, that is lambda star equal negative 10.5. So what this tells us is that indeed that approximate expression we had for lambda star is a pretty good one. So just to summarize, we went through the method for calculating characteristic root errors for different fixed step size integration methods for a first order dynamic system, and then provided some general guidance in terms of how to pick the integration step size h depending on the integration methods you're using. And here we looked at Euler and Trap, but you could do this for other methods using the same approach. So again, this is Gordon Parker from Michigan Tech, and thanks for watching.